Hello everyone, I'm Dhruv and now I will be presenting our project done in the course CS671. So our project was OPDX, Patient Medical History Aware Health Assistant. So this was our project team. This is me Dhruv Singh. Then we have Aryan Singh, Love Sharma, Satyam Kumar, Vivek Agarwal and our mentor Anushkrit Goyal. So this is the timeline of what we did on a span of 3 months, that is March, April and May. So the blue track here represents the work that we did on with LavaMed, and the green path represents the work that we did with MedLama, and the purple path represents the future aspects of our project. So when the project was assigned to us, first of all, we started with LavaMed, which was given to us by our mentor Anushkrit Goyal. So, what is LavaMed? So, LavaMed is basically a multimodal LLM. So, it basically consists of three parts. That is a pre-trained language model, a pre-trained image encoder, and a fusion layer. So, for the image encoder, we are using a vision transformer, and then we are using a Vicuna 1.5 13 billion as a pre-trained language model. So Vicuna is a LLM based on Llama 2 that is fine-tuned over shared conversations. And then we have a fusion layer between the image and the text space. So now let me explain you what I mean by the fusion layer here. So as you can see, this is the paper of Lava that was given by Microsoft Research. So as you can see, this vision encoder this vision encoder is used to map basically an image, that image vector, into a feature that is in the text space, and then the Vicuna is used to generate text output based on the user text input and image input. So now, why did we choose LavaMed? First of all, LavaMed is one of the only open source multimodal LLMs available, and it is fine tuned. It is trained on PubMed data and the self generated instruction following data by Microsoft Research. So this is what their self generated data looks like. So in one point of the data set, it consists of an image and then sequential conversations between human and the GPT. So GPT here is the supposed ground truth that the LLM should respond with. As you can see in this image, the human first of all asked what was in the image. Then there is a description of the image. So this was generated by GPT-4 Vision. So they generated the visual question answering data using GPT-4 Vision. And we tried to implement the LavaMed on a local machine using the GitHub repo that they provided. We faced several issues. So one of the first issues that we faced was the local compute limitations. So this model requires 24 GB just to load and take inference, and we did not have GPUs of that much VRAM. Even on Collab Pro, we were not able to run it for more than 1 hour. All the computer units were exhausted in about 1 hour only. And then, as this Lava Med is quite recent and only in development, there is no proper documentation available in their GitHub codebase, and we we were not able to take inferences using the Gradio chatbot in their code base, as it was disabled and it was having many open issues. So what was the solution to the problem that we faced? First of all, we transitioned to Param, the supercomputing facility at IT Mandi, to overcome the local compute limitations. And then we did lava modifications to the lava med code base, where we altered two files mainly, the test message.py and the model worker.py, to enable CLI inference mode. And we also implemented history. So as you can see, this was our implementation of lava made on in CLI mode on param. So here we gave a case study from any GMS data, and in this case study there is a 65-year-old woman with a history of depression, and she's having many problem, and then assistant has asked for a most possible diagnosis. So here it gave 10. So this was just plain lava made implementation on param CLI. Then even in this CLI, there was not the multimodal input was not enabled. We again made changes to the code base to enable multimodal inputs, and this was our implementation. We could give the URL of an image. So we gave an URL of the image of this human brain anatomy image, and we asked question what was in the image, so it accurately described the image. And as I said earlier, we had also implemented history. So when I asked again what was the condition inferred from this image, it uh, it used the previous history. So this was just the plain lava mat that we started with. Now our problem statement was to make a patient medical history aware health assistant. So then we came across one of the techniques used by doctors, that is known as differential diagnosis. So what is differential diagnosis? Differential diagnosis is a method by which a doctor asks several questions to the patient, his medical history and his antecedents, to illuminate many diagnoses and then finally arrive at one diagnosis. So this is one sample differential diagnosis uh, on COVID-19. As you can see, there are multiple if else's, and then finally doctor arrives on COVID positive or COVID negative. So this was differential diagnosis. So the lava mat that I just told you about, and other different medical LLMs or multimodal LLMs, they generally don't specialize in differential diagnosis. They have good biomedical question answering capabilities as they are trained on biomedical knowledge base, but the ability to make differential diagnosis and doctor like conversations is very much absent. So this was the importance and the relevance of DDX. So as you can see, it considers all possibilities to reduce the chances of misdiagnosing and then provide a targeted treatment. So then uh, we tried searching for a data set that was available that contained this differential diagnosis type of institute diagnosis done. So there were not many data sets available in the market. Only one, that is DDX plus data set, was available, and it contained hierarchical differential diagnosis. Unlike the other existing datasets that only considered symptoms, this DDX plus datasets also considered the past history and the antecedents, and they were organized very hierarchically. And it was a very rich data consisting of about 1.3 million patients and 49 pathologies, 110 symptoms, and 113 antecedents. And as I told you, this was a differential. This contained differential diagnosis. So this is what we were looking for. How the Myla Institute implemented DDX plus. So basically, what they did was they had a previous medical knowledge base. Then they calculated some census data, and some they also had prior distribution for different pathologies. So they statistically calculated different distributions for disease, symptoms, antecedents, and also the conditional distributions between disease and sex, disease, sex, age, and etc. So once these distribution were prepared, then we use a Cynthia. Then they use Cynthia to basically populate different patients from this distribution that they just created. So this synthesize artificial synthesized patient from these distributions contain the disease, symptoms, antecedents, race, age, and the geographical region also. So then they also had a telemedicine platform. They also prepared this telemedicine platform to give a differential diagnosis that was prepared using this particular distributions. So this was how they prepared DDX plus dataset. So this was DDX plus dataset, but we wanted to use it to fine tune LavaMed. But as I showed you earlier, this is a conversation type of data set consisting of sequential conversations, whereas this data set of DDX plus consists of different columns having one having several evidences encoded in E53 and etc. and initial evidence E201. So now let me explain you what all these means. So basically, E201 is an evidence encoded as a E201 character. As you can see here, every code represents a question in English. So this question represents, do you have cough, and if whether or not this is an antecedent or not. So this is one sample point, and for this evidences, there is a differential diagnosis given also. So, as I told you earlier, we need a conversation type of format. So, for that, what we would have to do is first of all create a parser to convert this type of data into a human readable text format. So, we created a parser using Python script to make a human readable summary of the patient from this CSV. And as I told you earlier, we needed conversational data, but this data also is not conversational. This just contains the initial evidence, symptoms, and the differential diagnosis. The conversational part of this is missing. So what we did was we purchased GPT 3.5 key, and then used the specific prompt to simulate conversation between a doctor and a patient while using this as the data. So the GPT 3.5, what it did was, from this type of data, it created a conversational data. So this is a simulated artificial conversation between a doctor and patient. So the doctor asks, "What are your symptoms?" Then the patient then says that it has chest pain, even address, and describes. So this is how it was described in this data set, and this is accurately transferred here in this conversation. So we prepared this conversation data set that was compatible with the LavaMed for fine tuning. So when we try to fine tune, we actually came across a CUDA out of memory error because the fine tuning of this LavaMed requires enormous GPU resources. It required 800 GPUs, each of 40 GB VRAM, and even on that, it would require 1 hour. So we faced CUDA out of memory error. So we were not able to directly fine tune this data set on LavaMed. So then we again revisited the architecture of LavaMed. So as I told you earlier, this LavaMed has three components: a fusion layer, a vision encoder layer, the pre-trained language model. So actually, a task, our data was more or less text only. So what we thought was, what we came up was that we could only use we could use a different language model instead of this Vicuna version 1.5 that was fine tuned on the data that I just showed you, and then swap it out with this Vicuna, and then use this as one whole lava med that was just text fine tuned on our custom data set. So now our second path begins where we did the work with medlama too. So as I told you, our strategy was now to swap out this Vicuna with a different fine-tuned LLM on a data set. So for fine-tuning a LLM on a custom data set, we first of all wanted a pre-trained model. So for the pre-trained model, we chose MedLlama 2. So MedLlama 2 is a LLM based on Llama 2 that is fine-tuned on MedQA dataset, and so why we use MedLlama 2? First of all, this is a Llama 2 variant, so it would be easier to integrate with the whole Llama Med architecture. And because DDX plus dataset only had the differential diagnosis capabilities, the biomedical knowledge base was not very much present in the DDX plus dataset. So that could be aided by using a pre-trained model on MedQ dataset which had biomedical capabilities. So this was so then we with the again we prepared the data set. So as I showed you, this dataset was compatible with LavaMed, but now we wanted to fine tune this MedLlama 2 on our dataset. So we again created a parser to convert that conversation into a LavaMed compatible into a MedLlama 2 compatible format. So as you can see, this is one of the points from the data that was used to fine tune the MedLlama 2. So there are two roles basically, assistant and the human. Assistant is basically simulating a assistant. In this, assistant is the doctor that I showed you previously, and human is the human that was previous in the conversation. This dataset was prepared for fine tuning the MedLlama 2. So even with the data set prepared, now we had the task of fine tuning MedLlama 2. So even fine tuning MedLlama 2 was not very cheap on the GPU compute end. So a full fine tuning of Llama 2 requires several A100s. So then we came across parameter efficient fine tuning, where we came across two techniques, that is LoRa and QLoRa. So uh, LoRa is basically a technique that reduces the trainable parameter. So what it basically does is, so traditionally while fine tuning, we store when we go from a initial weight to a final weight, we store the different weights. So what LoRa does is, instead of storing the final weight, it stores the changes that are to be done in the initial weights. So suppose you were initially storing a 100 cross 100 matrix of final weights. Now we would store 100 cross 100 matrix of the delta that would have to be done in the initial weights to arrive at the final weight. So even now we have 100 cross 100 matrix that we need to store in the GPU memory. So what LoRa did was, instead of using this 100 cross 100 matrix, it basically splits it into two matrices A and B. So each with dimensionality 100 cross 1 and 1 cross 100, which can be again which we can do, so we can do cross product on both A and B to arrive again on the same delta that was of 10,000 cross 10,000, sorry, 100 cross 100 dimensions. So by doing this we reduce the parameters significantly. So this was LoRa, and then QLoRa builds upon LoRa by quantizing the changes that are done in the weights to integer 4. And the paper QLoRa introduced a special data type called NF4. So basically it quantizes the weights into NF4 data. NF4 here represents the normal float 4. So this fine tunes the model with minimal loss in performance while significant loss in memory. So we were able to fine tune this Llama 2, Med Llama 2, sorry, Med Llama 2 on only 24 GBs of VRAM. So with the fine tune Med Llama ready, even getting inference out of these models is not very compute efficient, cheap on the compute end. Again it would require about 32 GBs of VRAM just to get inference out of this fine-tuned Medlama 2. So we came across a technique that is known as quantization. So quantization represents these weights that are generally stored in the floating point 16 format into a integer 4 or integer 8 format. So uh, this by doing this we achieve a significant drop in the GPU memory required for getting the inference with minimal loss in performance. So so our uh, so now our LLM had the DX capabilities. So we the problem statement of includes two parts: a patient medical history aware health assistant. So the health assistant part, that is the DDX capabilities that we had solved by using the DDX plus dataset to fine tune this. But to make it more patient aware, we would have to uh, use different uh, retrieval techniques. So then we came across RAG. So RAG was retrieval augmented generation. So basically, what it does is it stores the chunks of a document into a vector database, and according to our query, using a cosine similarity, it searches in the vector space for the most closest document in the vector database, and using this retrieve context, we generate the final output that is served to the user. So first of all, we try to implement an advanced retrieval technique that is known as adaptive RAG. So what adaptive RAG does is, when the user inputs a question, we do a query analysis. So the classifier basically uh, ranks the vector store as the are as relevant or not. So basically, this classifier, what it will do is, classifier is just a simple a small LLM that is used for uh, classification of the input, either that input belongs to the vector store or not. If it belongs to the vector store, then we use the vector store to retrieve and then generate. And if it is not relevant, then we simply do a web search to get the required context and generate the response. And even if the web search is not relevant, then we can simply use the LLM to generate an answer without retrieving any context whatsoever, and then final output is up to the user. So we had successfully implemented this adaptive RAG, but while testing, we saw that it would very you usually use the web search path for retrieving the context. And since our domain is medical, domain related to a patient's personal health, it is not safe to generate context using the web. So then we ditched the idea of adaptive RAG and implemented a simple multi-model RAG. So basically, what a multi-model, this was our pipeline. So when we upload the documents, we use the unstructured library to create different image chunks, the table chunks, and the text chunks from this document. The we use Lava. This is not Lava man. This is just plain Lava. So Lava Med was trained on the PubMed QA dataset. So and the Lava Med and the Lava is a general uh, multimodal LLM. So we use this Lava to generate image summaries of this images from the document, and and then store this image summary as vector in our chroma db. And then we apply our medllama to fine tune medllama to generate the table summaries and text summaries. So this llama here, this is not plain llama. This is the fine-tuned Med Llama 2 that we just talked about, the one that is capable of differential diagnosis to create a summary of different text and table that are present in the document. And whenever a patient would ask for a query, our multi-vector retriever would simply retrieve the relevant image or text or table summary, which is then augmented to generate a user that is uh, which is used to generate a output that is served to the user. So after implementing this multimodal rack, we try to solve some case studies using the ddx llama. So ddx llama here represents our fine-tuned medllama 2, the medllama 2 that we fine-tuned on our custom dataset, and gpt 3.5. So this was a case study from msd. So let me show you how this looks like. So this is a case study of a 49-year-old woman. So in this case study, a 49-year-old woman had a chest pain, and then there is a description of the patient, and then there are some review of the systems, the past history, physical examination, the first essential differential diagnosis, then the essential immediate steps that are required by the patient, the first test results, and very and then this interpretation of what was in the first test, and a very hierarchical type of case study. So we use this for testing here. So yeah, so when we gave this case study to our ddx llama, it predicted the accurate diagnosis. But when we gave this case study to ChatGPT 3.5, it produced an inaccurate diagnosis. And our model also recommended a D-dimer blood test to confirm or rule out the possibility of a pulmonary embolism. So this part here, uh, so as you can see, it makes differential diagnosis and also recommends the possible test, the immediate steps that are required. So this was possible because of the data set that we prepared from the DDX plus. So now let us have a demo. So what are the future aspects of this project? So first of all, we used only 10,000 conversations to fine tune this MedLlama 2. We can generate more conversations using this DDX plus dataset, and the DDX plus dataset only contains 49 pathologies. We can in the future aspect, we also want to create medical conversational data for more rare diseases and more rare case studies. And as I told you earlier, we wanted to swap out this pre-trained vicuna with this RDDX llama. So uh, after replacing this, there is an essential alignment required between the language model and the vision encoder and language model, uh, because the original fusion layer was between the plain vanilla llama 2 weights and a vision encoder, and now our weights have changed. So our MLP, the fusion layer, would have to be trained as well, but we cannot do this because of our compute limitations, as we only have as it require as this alignment requires about 800 GPUs. And we also want to test different retrieval techniques like knowledge graphs and different retrieval method like adaptive rag but improved. So as I told you, the adaptive rag had problem that it usually classified everything as web search and it was not safe. Then we want to improve this in our future respect. So this was OPDX signing off. Thank you.